piecewise functions. So a piecewise function is a function that it has different definitions for different parts of its domain. So for instance, if we were talking about just a line, right, that function is linear for all values of x that are within its domain. However, we can have functions that maybe from one section like -10 to 10 has one type of function, a parabola, a cubic function, a linear function, all sorts of things, absolute value, for instance. And then outside of that, it could be a constant or non-existent at one side and linear on the other, okay? So in order to define a piecewise function, we use this curly bracket, and then we have to tell it for what parts of the domain does the function follow a particular pattern. Now here they're going to ask us to evaluate the given values. So we have 3 values to plug in, graph the function, and then describe the range. So I'm going to manually graph, and then I'll show you a graph that I've already created in Desmos. So first it says to evaluate the given values. So f of 2. Okay, well, f of 2, first we need to figure out where does that fall within the domain. Well, this says x is greater than 1. So this guy, 2, obviously falls into that part of the domain, which means we plug it into that part of the function. So we're plugging in 2 plus 1, and we get 3. Then they ask us for f of -1. Where does -1 exist in the domain? Well, that would fall as something that's less than 1. So we would plug it into that portion. We have negative of -1 squared. -1 squared is 1. Take the negative of that, we get -1. The last one says, can you evaluate f of 1? Well, unfortunately, we can't. Notice that this is this is greater than 1. This is less than 1. Neither of those include 1, right? They don't say greater than or equal to or less than or equal to. Therefore, this function has a gap or an opening at 1. So this is undefined. Okay, let's go ahead and generate a graph. In order to do that, let's make a table of values. We're going to need to do this for each part of the domain. So let's do for x less than 1. Okay, and in my table, I need x values and I need y values, or f of x, right? Let's maybe start using that as our y. Okay, so if x is less than 1, we are using minus x squared. Let's pick some fairly simple values like 0, that's less than 1. -1, we've already done that. -2, and maybe let's do -3. So we plug 0 into that function. That's minus of 0 squared. That's still going to be 0. Then we have -1. So that's negative of a -1 squared. We've already done that. That gave us back -1. Do the same thing for -2 and -3. And give your results. So squaring a negative number makes it a positive. So this would be 4. And then take the negative of that makes it -4. And this would be -9. Okay. Then we need a table for x greater than 1. So let's generate that. We're doing greater than 1, so let's pick numbers like 2, 3, and 4. That should be enough. Okay. Now we are plugging them into this portion. So 2 plus 1, that's 3. And then we have 3 plus 1, that's 4. And we have 4 plus 1, that's 5. Okay. All right, let's concentrate on plotting those ordered pairs. Let's generate a graph. Let me get my Cartesian plane. It's always good to put your arrows and label your X and Y axes. Okay, so I'm looking for the ordered, no, so these ordered pairs are 0, 0, -1, -1, -2, -4, -3, -9. That's going to be a little off my graph because I don't have quite as many tick marks. So 0, 0, that's right here. -1, -1, -2, -4, and then -3, -9. So that's going to be down here somewhere. Now, one thing I didn't do is I didn't get very close to 1. So I started at 0, but this says it goes all the way up to 1, but doesn't equal 1. So what happens if I plug 1 into the function? What do I get close to? What am I approaching? So if I plug 1 into -x squared, that's going to be 1 squared, which is 1, and I take the negative. So that would be 1, -1. But I'm not equal, so I'm going to put an open circle. And you can see that this looks like a parabolic shape. And that should make sense, right? It's -x squared. That is, by definition, a parabola that has been flipped over the x-axis, what the negative does. Okay, so that looks good. What about the other part? All right, so here we have the ordered pairs 2, 3. And we have 3, 4. And 4, 5. So that's rather linear. Again, we need to know, what does this thing look like around 1? So if I plug 1 into there, I would get the point 1, 2. But again, an open circle. And that should be linear. Okay? So what's the domain here? We already said that we pick up all real numbers, right? The only thing we don't get is 1, right? We're not equal to 1. So we have to break that up. What about the range, right? What about the y values? So if I'm looking at y, it looks like I pick up everything as I go along here. Now, don't get confused, right? I have a closed circle here and an open one there, which means that value of y is in the range. So it looks like this continues on forever this way. And so I'm going from -infinity up to, and where do I stop? Well, the highest value I get to is 0. Then there's nothing in between here. And I begin again at 1, and I go on to infinity in the positive direction. And again, 1 is open. So I do not use a bracket, I use a parenthesis. Okay. So that's an example of how to evaluate a piecewise function, how to create a table and then generate a graph, and then look at the domain and range. So quickly, let me jump over to Desmos just so you can get a better picture of what this thing should look like. So I've already generated this in Desmos. And you can see I put the points 1, 2, which is right here, the purple, and the red open point, which is 1, -1, just to show that it's not equal there. And then you can see the line, or the parabola on the left side, right, for x less than 1, and it's a linear x greater than 1. So that looks just like the graph we generated. So everything looks good. Let's go ahead and move on to the next example. All right, so here's another example. Here we've got a piecewise function that has 3 parts. It has 2 linear portions and then one that's actually just going to be a point, right? It tells us that at x equal 3, y is equal to 7. So that's just going to be a point. All right, so first they ask us to evaluate just like last time. So what is the function at 2? Well, where does 2 fall? 2 is less than 3. So we would use this definition for that portion. So we'd have 2 times 2, and that's 4. All right, so next is f of -1. -1 is going to be less than 3 as well. So we're going to use the 2 times -1, and that's -2. Last, we want to know what is f of 3. Well, it tells us that when x is 3, f, the function, is 7. Okay. So they actually didn't give us an x value greater than 3 there, so we didn't use that middle portion, but that's okay. Right? We just demonstrated that we know where to put those things. All right, next we're asked to graph. So we need a table of values. So again, this is just a point. That's the point 3, 7. So I'm not going to bother doing any table for that, obviously. And then we are going to generate one for x less than 3. We've already done 2 of those. So that's nice. And we can do x and then f of x. So less than 3, we've already got -1. And that gives us the point -2. We've already got the point 2. And that gives us 4. Okay. Let's do maybe 1. So if we plug 1 in, that's going to be 2 times 1 or 2. And another value less than 3, let's pick 0. So 0, we get 0. All right. Let's go ahead and do the table for the next portion of the domain. X greater than 3. Okay. So again, I have f of x and x there. We need values greater than 3. So let's do 4, 5, and I think 6 will be enough. Let's see. So 4 minus 4 is 0. 4 minus 5 is -1. 4 minus 6 is -2. We can see where this is going to keep going to 7, -3, and so on. All right. And then, of course, we have the point 3, 7. So if we try to generate a graph, what does that look like? Okay. X and Y on my Cartesian plane. The tick marks. Okay. So let's plot this, or let's go ahead and do the point first. It was given 3, 7. So over 3 up 7. Okay, so it's going to be right here. And that's solid, right? Because it equals there. All right. -1, -2. +1, 2. +2, 4. 0, 0 is also a point. Okay, and then of course we need to go close to 3. So when we plug 3 into that part, that first part, 2 times 3 is 6. So when x is 3, we have an open circle at 6. And it's linear on this end. It goes on forever. All right. For the x greater than 3 portion, okay, let's go ahead and start at 3 this time. So 4 minus 3 is going to be 1. So 3, 1, and we have an open circle. Say approximately 3 on our table because we can't actually equal 3. Then when x is 4, we're at 0. When x is 5, we're at -1. 6, we're at -2. Okay, so we're linear on that end. Okay, so what values do we pick up for our range? Well, let's do domain first, just to be complete. So what values of x? Well, it continues on forever this way. We get x equal 3, and then it continues on forever that way as well. So the domain looks like it's going to be all real numbers, right? And the range, well, again, I'm looking for my y values now. So I'm going pick up everything. There's a hole there, but I also am equal on this end, so I'm okay. And I keep going, keep going. I have a jump here, right? So the only thing I don't pick up is between y equals 6 and y equals 7. Okay. So my range is going to look like this. From minus infinity to 6, be y equals 7. All right, so we can either say y equals 7, or we could do union 7, 7, which is kind of weird because it's at that point only. I'm not sure off the top of my head which your online homework is going to prefer, so I will give you both options. It's minus infinity to 6 and y equals 7, minus infinity to 6, union 7, 7. And I almost forgot, I wanted to show you the plot on Desmos. So again, I had already done that. Here's the nice pretty plot. That's much cleaner than the one that I created. And you got open there, and equal to here.